Our next segment in fluid statics is calculating the force against a wall that's submerged underwater. For example, the side of a pool wall. Let's say that the length of the wall is 10 meters, the depth is 2.8 meters, and how do we find the force against that wall? Well, using the equation pressure is equal to force divided by area, we can then rearrange the terms here and say that the force is equal to the pressure times the area. Now the problem here is that the pressure is not a constant, the pressure changes with depth. So the best way to do that then is to go ahead and imagine a small little strip against the wall that is at a depth of y below the surface and has a width equal to dy, and so therefore the force on that strip alone we can call a small amount of force df, and that small amount of force is equal to the pressure at that depth, which wouldn't change because the thickness is so small, times the area of that strip, and let's call that area a small little dA. And of course the dA is simply equal to the length L times the width dy. And so if we want to then find the total force, that's simply the sum of all the little strips, the force in all the little strips, and so therefore that's equal to the integral of all the little df's, which is equal to the integral of p dot dA. And now plugging in what these are, first of all, the pressure at any depth underneath the water is equal to rho g y. And so we substitute that in for p, and then dA, of course, will be the length times the width of each strip. So this is equal to the integral of rho g y, and dA would be equal to L times dy. And then you notice that in this integral, rho, g, and L are all constant. They come outside the integral, so this now becomes rho gl times the integral of y dy, and that's integrated from y equals 0 at the top of the pool, y equals 0, to y equals h, which is the depth of the pool. And then we go ahead and integrate that. Of course, the integral of y is y squared over 2. So this becomes then equal to, the force is equal to, let's see here, we still have rho gl. So that would be rho gl times the integral of y dy, which is y squared over 2, evaluated from y equals 0 to y equals the depth of the pool h. Of course, when we plug in 0, we get 0. So simply we plug in the upper limit, and so the force on that wall is equal to rho gl times h squared over 2. And then plug in the numbers. You want a numerical value. The density is equal to 1,000 kilograms per cubic meter. G is equal to 9.8 meters per second squared. L is the length of that wall, which is 10 meters. H was the depth of the pool, which we said was 2.8 meters. We have to square that, and then we multiply the whole thing by 1/2. And let's see what we get when we grab our calculator and plug in those numbers. So we have 1,000 times 9.8 times 10 times 2.8 squared, and divide by 2. And we have a total force of 384,160 newtons. Now, of course, those are not the correct number of significant figures. Since I gave you numbers with only 2 significant figures, we probably want to change that to scientific notation and write this as 3.8 times 10 to the, let's see, 1, 2, 3, 4, 5 decimal places, 10 to the 5th newtons, and that's probably a more accurate number, or a more appropriate number, I should say, not accurate, more appropriate number, considering the significant figures that we were using. Now also notice that even though we use integration to find the pressure or the force against the wall, what we could also do, since the pressure changes linearly with depth, what we could do is we can take the average pressure, and the average pressure would occur at the halfway point. So if we take the average pressure right here, P average, which is equal to the rho g times the average height or depth of the pool, we can then say this is equal to rho g times h over 2. That would then be the average pressure. And if we multiply that times the total area, we'll actually get the same answer. So let's see if we can do that. So we can say that the force is equal to the average pressure times the area. And the average pressure can be found by taking rho g h divided by 2. So rho g h divided by 2. And multiplying times the total area, which would be L times h. L times h, and notice we'll get the exact same equation that we had over here when we used the integration. So this can be written as 1/2 rho g L h squared. And then notice, of course, if you then plug the exact same numbers in here, you will also get the same result of 3.8 times 10 to the 5th newtons. So you can actually solve it like that as well.